In this series of YouTube videos, I want to explain what is digital command and control of model trains. And in the first videos here, I basically want to explain what DCC is and how it differs from the traditional DC or direct current method of controlling trains. So how does DCC differ from direct current? With direct current control of model trains, there's a steady voltage applied to the tracks, say plus 10 volts, plus 12 volts, plus 8 volts, and depending on the size of the voltage, that the train or the engine will either move faster or slower. If the voltage is removed, the engine will stop. So we've got this relatively steady voltage which will vary depending on what we want the engine to do. Now consider this scenario here on the left. We have a DC controller putting positive voltage onto the top rail and negative voltage onto the bottom rail. And in this situation, my engine will move forward. On the right hand side now, I reversed the voltage going to the rails. So negative goes to the top rail and positive goes to the bottom rails. And in this situation, the engine changes direction and starts moving backwards. So it's a very simple way and very effective way of controlling a single engine on a track. So DC is very good for that. The disadvantages of DC, however, are that if there's more than one engine on a track, say there's 2, 3, 4, 10, it becomes extremely difficult or complicated to measure or to control the engines and what they each individually do. And in this situation, we need to divide the track into separate subsections and apply different voltages to different subsections depending on which engines are on there. And as the engines move around the track and move from one subsection to another, the voltage from one subsection needs to change and move onto the next subsection. It becomes quite messy to control multiple engines with direct current. With digital command and control, however, the situation becomes much simpler. The same voltage or the same signal is applied to the entire length of the track. All of the track contains the same signal. There might be some scenarios where some sidings or some sub tracks could have different voltages, but on the whole we can ignore that in this discussion. So the voltage is the same all along the track, even if there is more than one engine on the track. And each of the engines, 2, 3, 5, 10 of them, can be controlled independently of each other without isolating different sections of track. In this scenario here, we have a DCC controller and engine number 1 is on the track. Also on the same track is engine number 2, controlled from the same DCC controller. The DCC controller sends a message to engine number 1 telling it to move forward, to move backwards, to go faster or slower, to stop. And this is totally irrelevant to engine number 2 because the message or the so-called packet is transmitted to engine number 1. Engine number 2 will ignore it. While engine number 1, say, is moving forward, the DCC controller sends another packet to engine number 2 telling that to go forward, to go backwards, to increase or decrease speed, or to do whatever the train owner wants it to do, without affecting what engine number 1 is currently doing and without isolating different sections of track. So what about the voltage on the track now with DCC? As I mentioned, with direct current control of engines, there's a steady voltage on the track, and the track is split up into different subsections, each quite likely having different voltages on them. With DCC, the voltage on the track is a series of plus and minus pulses. In my setup, I've got plus 12 volts and minus 12 volts. Now, depending on whether I want to send a digital 1 or a digital 0 along the track. If I want to send a digital 1, I send a plus 12 volt pulse followed by a minus 12 volt pulse, and the width of each pulse is 57 microseconds. If I want to send a digital 0 onto the track, I send another plus 12 volts followed by a minus 12 volt plus, but this time the width of the pulse is 100 microseconds. So by transmitting a series of pulses, plus and minus 12 volt pulses, with widths of 57 microseconds or 100 microseconds, I can send a string of digital 1s and 0s along the track to control the trains. So the DCC controller uses these plus and minus pulses to send digital 0s and 1s to instruct individual trains to move forwards at a certain speed, to stop, to move backwards at a different speed, to turn on or off lights, to sound its whistle. Okay, and the DCC controller can do this to different engines, as I mentioned, on the track without interfering to what's happening to the other engine. You send a command to engine number 2, engine number 1 will totally ignore that command, and I'll explain how this is done in subsequent videos. How does the DCC controller control a specific train? We have the DCC controller on the left. It sends what's called a packet of data to the train, to the engine, and on the engine is a DCC decoder. The DCC decoder picks up the signal from the tracks, determines if that packet is destined for this engine or not, in which case it'll act upon it. If it's destined for another engine, it'll ignore it, and it'll convert the digital data on the track into a control signal to the motor on the train, telling it to speed up or slow down or go forward or reverse, or telling the engine to put the lights on. So the DCC decoder converts any messages sent from the DCC controller into commands that the engine can act upon. So that is my overview of DCC. In subsequent videos, I'll explain in more detail how DCC works and to control your train.